Now, spoiler alert, I can't leave you hanging. I'm going to go ahead and do the solution for the actual position of the focal ray. But if you're going to work it out for yourself, hopefully you've already done it, or go away from this video and go ahead. I'm going to call this distance F, distance behind the lens at which the light focuses. So again, we have the triangle. This thing that you probably can't read here says delta x over r. Let's just write that a little bigger. That x didn't come out very well, but that's what it says. Hopefully you can read that one. It's not great. So if the focal length is here, the tangent of the angle is going to be this side over f. So there's the tangent of the angle. And the angle, being a small angle, is approximately equal to its tangent. So we have delta x over r here, and we simply solve that. We bring f over here, invert the delta x over r, and multiply. The delta x divides out. The r goes into the numerator. We have r times 2 over n minus 1. Very simple expression after all this. Now, let's go ahead and check that out for a set of typical numbers. We had r equals 5 centimeters. Delta x equals 1.25 centimeters. Let's see how some of these terms play out. Now, I've kind of got to wait for this board to dry, so I'm probably going to pause the camera here, pause the video a minute and come back. But let's just think about what this says. If r is 5 centimeters, delta x is 1.25 centimeters, then theta I, which is delta x over r, is 1.25 over 5, and that's going to be 1/4 or 0.25, so that your incident angle is going to be 0.25 radians. And if n is 1.33, as it is for water, then theta sub r, 1.33 is very close to 4/3, so we can kind of approximate the reciprocal of n as 3/4. So theta sub r is going to be pretty close to 3/4 of theta sub I. And that's going to be 3/4 of 0.25, and you can, it's 0.1875, I think. And you can work that out. You know, it's 0.75 divided by 4, and that does come out 0.1875. Okay, so that's our theta sub r. This distance A is going to be 2 delta x minus 2 delta x over n. We could factor out the 2 delta x, and we get 1 minus 1 over n. What's 1 minus 1 over 4/3? Well, 1 over 4/3 is 3/4, so that's going to be 1 minus 3/4 or 1/4. So we're going to be able to make all those approximations. Now I'm going to go ahead and do a lot of that over here, but I'm going to have to kind of lose part of this board, so I want to point out exactly what I'm doing. What's delta x minus a? Well, that's delta x times 2 over n minus 1. 2 over n is 2 over 4/3, which is 3/4 of 2, which is 3/2. We have 3/2 minus 1, that's 1/2. So that this delta x minus a, which is this distance here, if n equals 4/3, is going to equal 1/2 of the delta x. So that for water, this ray is going to hit very nearly at half the distance from the axis. Half delta x, half of this distance from the axis, which would be at 0.625 centimeters if our delta x is 1.25 centimeters. So all these numbers should reconcile with an analysis that's done with the actual numbers. And let me emphasize that actually, if you are fairly adept at symbolic analysis. The symbolic analysis is much simpler than the numbers because you can easily lose track of the numbers. Also, of course, the symbolic analysis applies if you have a different index of rotation. Mix some very strong sugar water, or find the index of refraction of some fairly transparent jelly, which has a lot of sugar, and you're going to get a higher index of refraction than you do for water. And you can check out the focal length and so forth. So if I summarize what we've gotten from the analysis and what we're going to plug in, R is 5 centimeters, N is 1.33, delta X is 1.25 centimeters. Theta sub I is X over R, theta sub R is X over NR. The delta X minus A, remember that's the distance from the axis at which the ray within the cylinder, the distance from the axis at which the ray from within the cylinder strikes the back of the cylinder is this, and simplifies as so. Then theta sub I prime is delta X over NR, and theta sub R prime is delta X over R. And all this follows rather simply. And here's the triangle that we analyzed at the end. The angle is delta X over R. If this is the focal distance from the back of the lens, then this side being the delta X minus A is delta X times 2 over N minus 1. And the focal position will then be R times 2 over N minus 1 relative to the back of the lens. So let's see what these numbers give us. Again, theta sub I equals X over R equals, and let me move this over so I'm not blocking it as badly. Theta sub I is X over R, which is 1.25 centimeters over 5 centimeters, which equals 0.25. Okay, now that's 0.25 radians. That's approximately equal to 23 degrees. And that's simply not right, so let's see what's going on. Don't know what I did to get 23 degrees there. 0.25 radians is about 0.25 of 60 degrees. That would be 1/4 of 60 degrees, and that somehow I was getting 24. I think I was dividing 60 into 25 or something like that. I did something really stupid, but 1/4 of 60 degrees would be about 15 degrees. Of course, a radian's somewhat less than 60 degrees, so we're going to reduce that to 14 degrees. Okay, now theta sub R is X over NR, which is 1 over N times X over R. Let's see, I'm going to say that's 1 over N times X over R, which is 1 over 4/3, using the 4/3 approximation. Of course, if you do this analysis, you want to use just a more accurate value for the index of refraction of water. But that's going to be 1 over 4/3, and we already found that X over R is 14 degrees. So that's going to be 3/4 of 14 degrees, which is 10.5 degrees. Okay, 1/4 of 14 is 3.5. Subtract 3.5 from 14, you get 10.5. Okay, so there's our theta sub R. So there's our angle of incidence and our angle of refraction. Now, the distance at which the refracted ray hits the back is delta X over NR. And looking without thinking, don't do that yourself. It's delta X multiplied by 2 over N minus 1. Once I wrote the delta x, it just kind of went on autopilot. And 2 over n, if n is 4/3, well, let's write it out. That's going to be delta x times 2 over 4/3 minus 1, which is delta x times 3/4 of 2, and that comes out 3/2 minus 1, which is 1/2 delta x. And we don't need to close the parentheses that we never opened. Okay, so 1/2 delta x, and that equals 1/2 of 1.25 centimeters. I don't have a good place to write that. That's going to equal 0.625 centimeters. Don't know how legible that is. Should be visible there at the bottom of the screen. Okay, and that's very close to what you get. I think if you do the 1.33 instead of the 4/3, this number comes out just a little bit bigger. So this comes out actually just a little more than 0.625 centimeters. Well, whatever. That's pretty close to what everybody gets. Okay, and then what? The theta sub I prime, the angle of incidence of the ray at the end, it's x over nr, which is the same as theta sub r, and let me stop and think about that and make sure that's right. Yeah, that's right. We want to maybe think a little more deeply about why this is equal to this. It comes out of the algebra. And I just noticed I didn't put deltas in my x's here. Let's try to make that work a little better. Okay. So that's equal to delta x over nr. We've already calculated that. We get that to be 10.5 degrees. So that theta r prime equals n times theta I prime, which is going to be 4/3 times 10.5 degrees, which is going to be 14 degrees, at least the approximation we're using here. I think it comes out more like 14.5 degrees, and this is 10.7 some degrees, 7, 8 degrees, or something like that. So we have theta r prime equals 14 degrees, and then finally, our focal length is, our focal distance is r times 2 over n minus 1, which is r times, we've already evaluated 2 over n minus 1 here and found that it's equal to 1/2 which is 5 centimeters over 2, which is 2.5 centimeters. This should agree with what we get if we actually do a numerical calculation throughout.